have this vision of what we want, and we're going to step backwards from that future state and work it back. Now, you might be thinking for a moment here, okay, well, that's just thinking about a future state and then figuring out the steps to get there. But it's not. What is most vital about this diagram, if we go back here for a second, is that we're going to do that in context of different possible scenarios. That's what we skip. So it's one thing to say, okay, what would we do if the world just keeps going on the trajectory that it's on to hit this carbon emission target? Cool. But what if we don't end up down that path? What if things go radically better or radically worse on certain metrics? What's the path forward from that? This is how we get resilience. Backcasting is the practical way to set out future goals. And I'm not going to say guarantee that you achieve them, but have a far more likely potential for a positive outcome because they are in context of different possible futures. Earlier this year or late last year, I read this book. If you don't know Neil deGrasse Tyson, you've missed out, and you are missing out. Please read some of his books or watch. He's got some shows and does a lot of talks. He's a quantum physicist, but a very accessible one, and probably would call himself an educator first. This particular book actually is to the person who, or the group that talked about the decline of civility. This is his manifesto for civility, actually, in a way. It's actually not a book about science or physics for the first time. There's one thing that I really took away from this book that stuck with me. He argues that every 30 years, which is roughly a generation for humans, every 30 years, the world is unrecognizable. Let's go to 2020 and forget about the pandemic for a moment. If you were in 2020 and you took a person from 1990 and you time travel them to 2020, they wouldn't have a clue what we were talking about half the time. They wouldn't understand what a smartphone was. It would seem like a Star Trek-ish device. They wouldn't know what Googling something was. They wouldn't be able to text you. Technology has transformed things, but it's not just technology, because you can make the exact same argument between 1960 and 1990, between 1930 and 1960. Every 30 years, at least going back the last 100, maybe 150 years, the world is essentially unrecognizable to us. So let's talk about what that means as we look ahead a little bit. So let's go back for a moment. 1997 was a spectacular year. A lot of great things happened. Man of the Year. Back when they did like a Man of the Year, and I don't know if there was a separate Man of the Year, Woman of the Year, or just Person of the Year, but it was George Clooney. First Harry Potter book. Not movie. Book was published. J.K. Rowling now has more money than the royal family. She's very, very wealthy from a series of books about a magician. Who would have thought? Titanic sailed into theaters and into our hearts. And you're lying if you say you didn't go see it in theaters, or at least once, probably twice. This is objectively not a great movie. I rewatched it recently, but I saw it in theaters twice as a kid. So, but probably the most interesting thing that happened to me was a game of chess between, at the time, or he still is a grandmaster, but at the time, world champion, world grandmaster Gary Kasparov against IBM's supercomputer Deep Blue. It was the first time a computer had beat the world's best chess player. And I love this photo because I kind of feel sad for him. He looks utterly defeated. And if you happen to play chess or have played chess and you look at the board, he's actually very, very early in the match. And he already looks utterly crushed. So how did that work? Well, it actually wasn't such a big deal. That computer at the time, which, by the way, each of your rectangles in your hand has more computing power than Deep Blue did in 1997, could do about 20 billion calculations, which equated to 12 moves and counter moves, 24 moves of chess in the time allotted for one move of play. So what it was actually doing was imagining 24 different possible future states of the board, 24 combinations of moves. But it wasn't doing one path of those 24 moves. It was doing all of them. The computer calculated every possible state that that board could be in 24 moves in the future, and then just picked the best position and did the one step toward that. We call it, in computer science, we call it brute force. It's like guessing someone's iPhone password by typing in 00000001. By your 10,000th guess, actually on average, by your 5,000th guess, you will have revealed their password. It's a brute force attempt. And that was all good and fine. And the media at the time was, you know, computers going to take over everything, artificial intelligence, this and that. And then we look back and it was a bit of an overcorrection, overhype. Fast forward 20 years, actually 21 years. In 2018, Lee Sedol, the world's best at the time rated player of the game Go, was defeated by Google's algorithm, AlphaGo, in a regulation match of this game. It took us 20 years to build a computer that could beat someone at chess, to get to a computer to beat someone at Go. The funny thing is the rules of Go are a lot simpler. There's only one big difference. The board is bigger. It's not a whole lot bigger, but it's so much bigger that there is 10 to the 170 possible combinations of moves. So for those who haven't done their scientific notation in a while, that's a 1 with 170 zeros behind it. Possible moves. There are only 10 to the 80 atoms in the entire known universe. It would take until the end of time to do a brute force attack and you still wouldn't be done. So the computer had to do things differently. We had to go from system intelligence that was based on logic to one that was based on intuition. Enter the next step in the evolution of AI. In fact, during one of the matches, because I think it's best, it's either 2 out of 3 or 3 out of 5, the commentator, and yes, professional Go commentator is a job that somewhere someone has. That's probably one of them, but the commentator made a note. The computer did a move and said, oh, rookie mistake. No one plays that strategy anymore. Lee's definitely going to win this match. A dozen moves later, Lee resigned. The computer wasn't doing what even the commentator thought. The computer had improvised a new strategy, one that is now, if you were to go read a modern Go textbook, which please don't, unless you really like the game, you'll actually see that that strategy is now named after some of the founders of Alpha, which was a company before Google there, because it's actually a really, really good strategy that humans had never come up with. The computer actually improvised a new approach. That should scare us. We are now living in the age of generative AI. I'm not going to regale you with all the cool things that Lexicart and DALL-E and ChatGPT and WriteSonic can do. If you haven't played with the tools, go do it. But I want to share with you one example of where this is going, because I think this relates a lot to planning and should scare you a little bit, should make you maybe a little bit excited. I'm only going to play 1 minute of this video.
Okay, I'll share one more project. This one's a little bit crazy. We're working with Amsterdam-based artist Joris Laarman and his team at MX3D to generatively design and robotically print the world's first autonomously manufactured bridge. So Joris and an AI are designing this thing right now as we speak in Amsterdam. And when they're done, we're going to hit go, and robots will start 3D printing in stainless steel, and then they're going to keep printing without human intervention until the bridge is finished. So as computers are going to augment our ability to imagine and design new stuff, robotic systems are going to help us build and make things that we've never been able to make before.
So I go back and forth every time I think about this example about which part scares me more. Is it that the computer designed the bridge or that it built it? And I think it's actually the both. If a computer had designed the structure for the bridge and that team of engineers and construction professionals had built it, I think that'd be one thing. I think if a bunch of really smart engineers got together, designed a bridge based on modern bridge design standards, and then a computer built it, I feel a little bit more comfortable. I think it's in that both, but this is a data point. This is one of those things that in 5 years from now, you might be in a room just like this or with a team doing a foresight exercise, and you'll be writing down, in 2023, we heard about this bridge that was autonomously designed and built. And now that's how we're building not just bridges, but entire buildings. What does that mean for planning? What opportunities does it open? What threats and risks